Trigonometric functions are all periodic, which means inherently they repeat their output values over the pattern of their output values on a fixed interval. We know this very well from establishing the graph of the sine function or any of the others, that we can plot a few points to complete one period of the graph and then just extend that pattern endlessly. So that means that in order to create the inverse functions for each of the trigonometric functions, we need a very drastic reduction in the domain. So the functions are definitely not one-to-one. They fail the horizontal line test miserably. So we have to cut away a huge portion of the graph of any of the trig functions. So we'll start with the sine function. It's usually the first of the trigonometric functions discussed. It is very simple and basic in how it works and very familiar. So we have the graph of the sine function up here, centered at the origin. Not too much of it, but enough to suit our purposes. So let's start by defining the characteristics of the sine function, because the inverse sine function is awkward. You know, much like logarithms don't make a whole lot of sense on their own at first. You really need to think of them in terms of the exponential that it is the inverse of. So let's make sure we clearly understand what the sine function is. Now, the input to a sine function is always an angle in radians. It is always an angle measure. For all of the trig functions, the input value is always an angle in radians. The output value here is a y-coordinate on the unit circle. Now, those are things that we should know pretty well, but in any case, it helps to have them written down there. It will help especially as we go towards the inverse function to understand what it is we're looking at there. Now, the domain of the sine function is all real numbers. That is to say, we can take any angle you can possibly imagine, positive or negative, fraction, decimal, whole number, an angle in terms of pi, an integer angle, anything, literally any angle you can imagine, and there will be a y-coordinate on the unit circle for it. There always is. However, as we go around the circle multiple times, we tend to repeat some of those y values. Actually, even in a single rotation of the circle, we still repeat some of those values. So, we obviously, in order to make it one-to-one, are going to have to not allow endless rotations around the unit circle for our angles. Now, there are a few guidelines to follow when you are restricting the domain of a function in order to make it one-to-one. The first most important thing is that we are not supposed to alter the range at all. So let's take a quick pause here and establish the range of the sine function. The y-coordinates on the unit circle can never go below -1 and never go above +1. Hence the unit circle centered at the origin with a radius of 1. You can never go more than one space in any direction, directly up or directly down. So in restricting the domain, we're not allowed to alter that. The point is to prevent repetition of y values, not to eliminate any y values from the range. So at some point, we have to go up to the highest possible y value and down to the lowest. Now, the next important guideline is that we want to include the central point of the function. Any basic function has a central point of x equals 0. Even in something like a rational function where there's an asymptote there, that's still kind of considered the center of what we're doing. But we want to keep that central point whenever possible. That being said, we then sometimes, not in this case, but sometimes we'll have a choice of choosing, do I want the left side of x equals 0 or do I want the right side? And the third guideline is, if you have that choice, take the positive side. That won't be an issue in this particular function, but we will see that in dealing with cosine or dealing with secant. Now, here's the trick. We know we have to keep the entire range, so we have to go as far down as -1, we have to go as high up as +1. And the second guideline is we have to keep the central point x equals 0. So that really kind of makes the restriction for us. We want to keep the central point of x equals 0, and from there we have to extend up to our highest y value and down to our lowest. Now, can I go any further than that? Well, the answer really is, I hope fairly obviously, no. The whole idea of hitting a peak or a maximum point on a graph is that you have to go up the one side and then come back down the other. And as the old adage says, whatever goes up must come down. Whatever output values you produce on the way up, you're going to have to produce those same y values on the way back down. So the way to prevent that from happening is to literally just stop the function as soon as we hit that maximum. We get the same effect on the left side. We can go down to this point where it bottoms out, this minimum, but the second we pass it, we're going to have to repeat the same y values we had on our way down, going back up. So we have to extend down to this point to maintain the original range, but we cannot extend beyond it. So what we get is a restriction from -π/2 to +π/2. And we can include those points because we can hit the original maximum and minimum output values of 1 and -1. We just cannot go past them. So our restriction will be the interval, the closed interval from -π/2 to +π/2. Now, the inverse function. The inverse function has two notations. In keeping with other notations for inverse functions, we use this, it's not really an exponent, but it is a superscript. It's written in the same position an exponent would be written, of -1. It indicates an inverse. It is not an exponent. However, I do recognize that it is easy to confuse that with an exponent, and that leads to some issues. Like here, this is the notation, one of the notations for the inverse sine function. But the other place we see a -1 exponent is in reciprocals. And there's a very big difference between the reciprocal of sine, which is cosecant, and the inverse of sine. Very, very different functions. So I don't really like this notation so much. I find it to be very easily confused with reciprocation. There is another option, Arcsine. I prefer the arc notation, the arc functions for referring to the inverse trig functions, because they don't have that confusion with reciprocation. There is nothing else that has an arc in front of it like that. So where does the arc come from? Why is it arc sine? Well, that's part of where it will help to have an understanding of what the inputs and outputs are. Remember, in inverse functions, the roles of input and output swap. So the inputs of the inverse or arc sine function are y coordinates of the unit circle. And the output then is an angle in radians. Now, to go with that, the domain and range have to flip-flop as well. So the domain of the arc sine function will be -1 to 1 to match with the range of its inverse. Now, the only way this inverse exists is if we look at only the portion on which the original function is 1 to 1. So this domain, while true for the original sine of x, we have to use its restriction in order to create the inverse. So the range of the arcsine function is negative pi over 2 to positive pi over 2. So again, why arcsine? Well, part of the idea of radian measurement is that on the unit circle, the angle measure is actually equal to the arc on the circle. So for example, just going to draw a quick circle here. Not an artist, you'll have to forgive me. This angle, pi over 4, which we usually mark in here because when we're using degrees, that is the appropriate place to mark where the angle is. And there's nothing wrong with doing that with radians either. But on the unit circle, when that radius is 1, the unique thing is this arc, that arc length is also pi over 4. On the unit circle, the angle measure in radians and the arc length are actually exactly the same thing. Hence the word arc. This literally then translates as, what is the arc of the circle that has a sine value of whatever this is? Literally, what arc or angle, what is the arc or angle that has this y coordinate on the unit circle? In that way, the arc notation is easy to interpret. It literally reads in that way, and it also doesn't confuse with the reciprocal by using that -1, that thing that appears to be a -1 exponent but isn't really. Mathematicians love to use confusing notation. I don't know why, but we do. So I prefer to use the arc notation, and I will use that pretty exclusively just for consistency. So this is the arc sine function and its characteristics.